The cloud is a lie. How the internet actually works under the ocean. You are holding your phone right now, perhaps watching a high-definition video streaming instantly from a server located halfway around the world. You look at the top corner of your screen and see a little Wi-Fi symbol, or perhaps a 5G icon. You save a photo, and your phone tells you it is safely stored in the cloud. This language, these icons, they have created a collective, global illusion. We have come to believe that the internet is a wireless, ethereal thing. A magical network suspended in the air around us, beaming data down from satellites like divine knowledge. That is a complete myth. The internet is not in the clouds. It is under the ocean. And it is not wireless. It is incredibly, heavily, brutally wired. Welcome to the hidden physical reality of the global internet infrastructure. The biggest misconception people have is about the scale of wireless technology. Yes, the connection from your phone to your Wi-Fi router in the next room is wireless. That travels a few meters through the air using radio waves. But the moment that signal hits your router, the wireless journey ends. It turns into electrical pulses, travels out of your house, down the street, and eventually joins a massive bundle of physical cables. If you are viewing content hosted on another continent, say, you are in Europe watching a YouTuber based in Japan, that data does not bounce off a satellite. Satellites account for less than 1% of global internet traffic. They are too slow, too expensive, and have too much latency, signal delay, for modern demands like gaming or 4K streaming. Over 99% of all international data travels through physical cables laid flat on the bottom of the ocean floor. When we talk about the cloud, we are actually talking about someone else's computer in a massive, air-conditioned warehouse somewhere else on Earth, connected to you by a very long, very wet wire. To understand how this works, we have to abandon electronics and start talking about photonics. The backbone of the internet doesn't carry electricity over copper wires like the power grid. It carries light. The core technology here is fiber optics. Imagine a strand of glass that is pure silica, thinner than a single human hair. Now, imagine billions of bits of information, zeros and ones, being converted into rapid pulses of laser light. Laser flashing on means 1. Laser off means 0. We shoot these lasers down that thin glass strand at phenomenal speeds. But how does the light stay inside the glass? Why doesn't it just shine out the sides of the fiber and get lost? This relies on a fundamental principle of physics called total internal reflection. It's the same phenomenon you see if you are swimming underwater in a pool and look up at the surface at a shallow angle. The surface looks like a perfect mirror reflecting the bottom of the pool. The core of the fiber optic cable is made of ultra-pure glass with a high refractive index. It is surrounded by a different type of glass called cladding, which has a lower refractive index. When the light signal tries to escape the core and hits the boundary with the cladding, it doesn't pass through. Because of the difference in refractive indices, it bounces perfectly back into the core. The light zigzags its way down the fiber, bouncing off the walls for thousands of kilometers. While light in a vacuum travels at roughly 300,000 kilometers per second, light inside glass travels about 31% slower. Still, it is the fastest, most efficient way to move information ever invented by humans. But sending one color of light down a fiber isn't enough for the modern internet. We need more bandwidth. This leads us to another incredible piece of physics, dense wavelength division multiplexing, or DWDM. Imagine a highway with only one lane. Only one car can travel at a time. That's a single laser. Now, Imagine expanding that highway to 100 lanes stacked on top of each other. DWDM allows engineers to send multiple different colors, wavelengths, of laser light down the exact same fiber strand simultaneously without them interfering with each other. Your Netflix movie might be encoded on red light, while someone else's email is encoded on blue light, and a bank transaction is on green light, all traveling down the same hair-thin glass fiber at the same time. At the other end, a prism separates the colors back out. This technology means a single modern undersea cable can transmit tens of terabits of data per second. That is enough to transmit the entire digitized contents of the Library of Congress in seconds. Now, take those delicate glass hairs and put them at the bottom of the Atlantic Ocean. This is the engineering miracle of submarine cables. A typical undersea cable is only about the thickness of a garden hose. But inside, the actual fibers are tiny. The vast majority of that thickness is armor. The fibers are encased in jelly to protect against water intrusion. Then comes a copper sheath. Why copper if it doesn't carry data? Because light fades over distance. Every 80 kilometers or so, there is a submerged amplifier that boosts the light signal. That copper sheath carries high-voltage electricity, up to 10,000 volts, from land to power those underwater repeater stations. Around the copper are layers of steel wires for tensile strength, so the cable doesn't snap under its own weight when being lowered kilometers down to the seafloor. Finally, it's coated in thick polyethylene plastic. Why so much armor? Because the ocean floor is a hostile environment. Cables are laid by massive, specialized ships that spend months at sea, slowly unspooling thousands of kilometers of cable. Near the shore, where fishing activity is high, underwater plows bury the cable under the sand. In the deep ocean, they just rest on the seabed. They are constantly under threat from underwater landslides, earthquakes, ship anchors dragging on the bottom, and yes, occasionally sharks bite them due to the electromagnetic fields, though that is rare nowadays due to better shielding. There are over 550 of these active cable systems stretching more than 1.4 million kilometers around the globe. They are the physical nervous system of our planet. But having the pipes is not enough. You need a traffic controller. How does a pulse of light leaving New York know how to get to a specific laptop in Tokyo? It is not a direct line. This brings us to the brain of the Internet, BGP, or Border Gateway Protocol. The Internet is not one giant network owned by one company. It is a patchwork quilt of tens of thousands of independent networks, ISPs like Comcast or AT&T, universities, governments, and tech giants like Google and Amazon. These independent networks are called autonomous systems. BGP is the language these systems use to talk to each other and figure out maps. There is no central map of the Internet stored anywhere. Instead, every major router constantly tells its neighbors, "Here are the IP addresses I can reach, and here is how fast I can get there right now." When your data packet enters the Internet, routers look at the destination address and make an instant decision based on the current BGP information. The fastest route to Tokyo right now is via this cable to London, then across to Mumbai, then up to Japan. 5 seconds later, that route might change because a cable got congested or damaged by a fishing trawler. Your data is constantly being shuffled around the globe, hop by hop, router by router, finding the path of least resistance in milliseconds. These networks physically meet and exchange traffic in massive, highly secure buildings called Internet Exchange Points, IXPs. These buildings are the physical crossroads of the digital world. So, how does understanding this physical infrastructure help you use the Internet better? Here is the utility protocol for navigating the wired world. First, the DO protocol. Do prioritize wired Ethernet connections for anything critical. We just learned that light and glass, fiber, is the gold standard of speed and reliability. Wi-Fi is just radio waves through air. It is subject to interference from thick walls, microwave ovens, baby monitors, and your neighbor's router fighting for the same frequencies. Wi-Fi adds latency, lag, and instability, no matter how expensive your router is. If you are competitive gaming, day trading stocks, or hosting a critical video conference, plug an Ethernet cable directly into your router. Get as close to the physical fiber network as possible. Don't rely on the air gap if stability matters. Second, the DON'T protocol. Don't panic when you hear news about an undersea cable being cut. It happens frequently, dozens of times a year globally. Because of BGP, the internet is designed to be resilient and self-healing. If one major cable across the Atlantic is severed by a ship's anchor, the BGP routers instantly notice the dead end and automatically reroute traffic to the remaining operational cables. Things might get slightly slower due to sudden congestion on the remaining paths, but the connection between continents won't totally fail unless multiple redundant systems are destroyed simultaneously. The system is fragile locally. A single cut breaks a cable, but it is incredibly robust globally due to redundancy. Third, the WAN protocol. When diagnosing slow internet, understand the bottleneck hierarchy. Before you blame the global internet or the undersea cables, look locally. The bottleneck is almost always the last mile. This is the connection from your ISP's local hub to your specific house. The massive undersea fiber pipes have insane bandwidth, terabits per second. But your home connection might still be using old copper phone lines, DSL, or shared coaxial cable. Your home connection is a tiny soda straw compared to the fire hose of the global backbone. If your internet is slow 99 times out of 100, it is your modem, your router, or the line coming into your street, not the transatlantic cable. Always test with a wired connection before you call your ISP to complain. In conclusion, the internet is not magic. It is not a cloud. It is a staggering feat of mechanical, electrical, and optical engineering. It is a tangible machine made of glass, steel, copper, and light, stretched across the most inhospitable regions of our planet's surface. The next time you tap a link on your phone and a website loads instantly from thousands of miles away, remember that you just sent a flash of laser light on a perilous journey beneath the sea, bouncing billions of times inside a glass hair, just to bring you that information.